So, it's been over 2 weeks ever since my last upload. I've been on vacation and on a math grind. I just did problems in the car and hotel. But I'm back, and I have a pretty interesting problem to share. We're going to let n be the number of ordered triples of positive integers, a, b, c, for which this equation holds. Now, you want to determine whether if n is even or odd. Now, for clarification, when I say ordered triples, I mean the order of the numbers in this triple matters. So for instance, if 1, 2, 3 was a solution, then something like 2, 1, 3 would be considered a different solution because the order of the numbers is different. So these are different solutions. We'll consider them. Okay, so we want to determine whether if n is even or odd. Now, our first instincts might be to, just somehow solve the equation, find all possible solutions, and count them all up. But that's not going to be easy. And if the intended solution was to really find all the solutions and count them up, what a weird query this would be, right? It would also make it a lot easier for me to communicate this problem through the thumbnail and title. So hopefully that's enough to convince you that there's a more clever strategy we can use. So what can we do? Well, instead of trying to figure out what A, B, and C can be exactly, maybe consider some possible solution formats. So for example, consider a format in which all the numbers are different. So we have A is not equal to B, B is not equal to C, and C is not equal to A. Under this condition, how many solutions will there be? Well, we're not sure, right? But we're going to call the number of solutions n1. Now, here is something I'm going to say. Even though we cannot find n1 easily, we can find its parity, meaning we can find whether if it's even or odd pretty easily. Why? Well, if A, B, and C are all different, then consider this. If you have a certain solution, A, B, C, then since we're considering ordered triples, then how many permutations exist? 6 factorial permutations, right? Not 6 factorial, what am I writing? This is what happens when you're gone for 2 weeks. 3 factorial permutations, right? So therefore, 3 factorial is equal to 6, which is obviously even. So n1, even though we don't know the exact value, we know that this is for sure even. So, even though we might not know exactly what n1 is, we know its parity, which, as you can guess, is more than enough for a problem like this. So, as you can probably see, our strategy is going to be just to consider the format of the solutions and to consider their permutation count. So, this was case number 1, when all of them were different. What about, case number 2, where we have exactly two distinct values among A, B, and C. So for instance, we can have a format like A, C. For brevity, I'm going to let the number of ordered solution sets be n2 for this case. Now, is n2 even or odd? Well, consider that if we had a solution like this, then the number of permutations would be 3 factorial, and then you divide by 2 factorial, because there are 2 duplicates there. So this would mean that there are 3 permutations for a specific solution triple of this format. Now, with an odd permutation count, we can't instantly say whether if n2 is even or odd. Whether n2 is even or odd depends on the number of unordered triples of solutions for this case. How do we find those unordered solutions? We can actually do that pretty easily. Check this out. If A and B were equal, then our equation would become 2 over A plus 1 over C is equal to 1, right? And now we can clear denominators. So then we would get 2c plus a is equal to ac. And then you can move this ac over, so you get 2c plus a minus ac is equal to 0. And then here we can perform a factoring trick. Basically, what you do is you can first take out this a among these two terms. So that's 1 minus c over here. I'm running out of room. But then as you can see, we can actually complete the factoring. Do you see how? Well, if we subtract a 2 on both sides. Then our equation becomes 2c and then minus 2 plus a times 1 minus c is equal to negative 2. And you can see that when we take out 2 from this becomes 2 times c minus 1. And we can take out a negative 1 from this bracket, so that's negative a times c minus 1 is equal to negative 2. We can easily factor c minus 1 out. So this becomes c minus 1 times 2 minus a is equal to negative 2. And this is a very easy equation to solve, because since c and a are both integers, positive integers actually, then these two must be factors of negative 2. So yeah, there you go. You can easily, check for factors of negative 2 and then deduce solutions for a and c. So, as I said, when you consider factors of negative 2, you will get these two solutions. Now, notice that 3, 3 is not valid because we want a and c to be different. So this is not going to be valid. So we only have this one. And notice that this pair corresponds to the triple 4, 4, 2. Okay, sorry, why are there smudges? So anyways, this pair corresponds to this triple, right? So we can see that there is only one triple under this case number 2. So therefore, this is odd. The number of unordered solutions is odd. And odd times odd, right? Odd times odd, well, that's going to be odd. So therefore, n2 is going to be odd. We've deduced the parity of n2. We only have one more case to consider. And that case is really, really trivial. This case number 3 is when all are the same. When all of A, B, C are the same, well, there's only one. The only possible solution is, well, A equal to B is equal to C is equal to 3, right? So there's only one, which is obviously going to be odd. And therefore, we've considered all cases. We have an even case, we have an odd case, and we have an odd case. Odd plus odd is even plus even is even. Therefore, our answer is that the number of, n is going to be even. And that is going to be our answer. So, I used up a lot of the board, but as you can see, the key insight was maybe, don't think about the solutions themselves. Think about how you can break them up into cases that will be easier to consider for the context of this problem. So that's going to be it for this video. I hope you enjoyed it. I hope you found it interesting. If you did, then please consider dropping a like and subscribing. Thank you very much. Bye.